cosm. Whoosh.
Imagine standing in the middle of Times Square on New Year's Eve. The noise, the chaos, the overwhelming sensory experience. Now imagine that Times Square is a galaxy, and instead of confetti and champagne, it's shooting jets of superheated plasma millions of light years into space at nearly the speed of light. Welcome to Radio Galaxies, the universe's most spectacular cosmic fireworks show that you can't see with your eyes, but your radio telescope? That's a different story. Here's something that'll blow your mind. Right now, as you're listening to this, there are galaxies out there in the cosmos that are screaming at us. Not with sound, of course, because space is a vacuum, and we all know sound can't travel through a vacuum. But with radio waves, powerful, thunderous radio waves that dwarf anything we've ever created on Earth. These aren't your grandmother's AM radio signals. These are torrents of electromagnetic radiation so intense that a single radio galaxy can outshine billions of stars combined, but only if you're looking in the right part of the spectrum. Let me paint you a picture. The year is 1931. A young engineer named Carl Jansky is working for Bell Telephone Laboratories in New Jersey, trying to track down sources of static that might interfere with radio communications. He builds this rotating antenna system, basically a merry-go-round of metal and wire, and starts listening to the sky. And then he hears it, a persistent hiss that seems to come from the center of our galaxy. Carl Jansky has just discovered cosmic radio waves, and with them, he's accidentally opened a door to an entirely new way of seeing the universe. He didn't know it then, but he'd found the first whispers of something far more powerful lurking in the depths of space. Fast forward to the 1950s. World War II is over, and suddenly we've got all this military radar technology just sitting around. Astronomers, being the opportunistic bunch they are, point these new radio telescopes at the sky and start cataloging radio sources. They find thousands of them. But here's where it gets interesting. When they match up these radio sources with optical telescopes, trying to see what's actually making all this noise, they discover something nobody expected. Many of the brightest radio sources aren't coming from within our galaxy at all. They're coming from distant galaxies, billions of light years away. And the structure of these sources? Absolutely bizarre. Picture this, you're looking at a galaxy through a radio telescope. You'd expect to see, well, a galaxy-shaped blob, right? But instead, you see two enormous lobes of radio emission, extending hundreds of thousands, sometimes millions of light years on either side of a tiny central galaxy. It's like the galaxy is wearing cosmic Mickey Mouse ears, except these ears are larger than thousands of Milky Ways stacked side by side. This is your classic radio galaxy, and it's one of the most magnificent structures in the universe. So what's going on here? What could possibly create such a monstrous cosmic architecture? The answer lies in one of the universe's most fascinating and terrifying objects, the supermassive black hole. And I know what you're thinking. Black holes are supposed to suck everything in, right? They're cosmic vacuum cleaners from which nothing escapes. And you'd be right, mostly. But here's the plot twist. It's not what's going in that creates these radio jets. It's what doesn't quite make it in. At the heart of nearly every large galaxy, including our own Milky Way, there's a supermassive black hole. We're talking millions to billions of times the mass of our sun, compressed into a region smaller than our solar system. Now, most of the time, these black holes are pretty quiet. They're on a diet, barely snacking on the occasional star or gas cloud. But sometimes, and this is when things get really interesting, they get hungry. Really hungry. When a supermassive black hole starts actively feeding, gobbling up vast amounts of gas and dust from its surroundings, that material doesn't just fall straight in. It forms what we call an accretion disk, a swirling vortex of superheated matter spiraling around the black hole like water going down a cosmic drain. And here's where the physics gets absolutely wild. That accretion disk becomes so hot, so energetic, that it heats up to millions of degrees. We're talking temperatures that make the core of our sun look like an ice cube by comparison. Now, you'd think all that material would just eventually fall into the black hole, and a lot of it does. But nature has other plans. The combination of the black hole's rotation, its powerful magnetic fields, and the extreme physics happening at the edge of the event horizon creates something that seems almost impossible. It launches jets, powerful, collimated beams of particles and energy that shoot out perpendicular to the accretion disk, above and below the black hole, at speeds approaching the speed of light. Think about that for a second. A black hole, the universe's ultimate consumer, somehow becomes a cosmic particle accelerator and fire hose, spraying jets of superheated plasma across millions of light-years of space. It's one of the most spectacular examples of nature's ability to take a simple rule, gravity pulls things together, and create something of breathtaking complexity. These jets are not subtle. We're talking about beams of particles carrying more energy than our entire galaxy produces in the same time frame. As these jets tear through space, they're traveling at relativistic speeds, meaning they're moving so fast that Einstein's special relativity becomes critically important. Time literally slows down for the particles in these jets compared to the rest of the universe. If you could somehow ride along with one of these particles, millions of years might pass in the outside universe while only days pass for you. That's the power of moving at 99.9% the speed of light. But here's where radio galaxies really show off. Those jets don't just disappear into the void. Eventually, after traveling hundreds of thousands or even millions of light years, they slam into the thin gas that exists between galaxies, the intergalactic medium. And when they hit, they create enormous shock waves, heating and compressing that gas into vast bubbles or lobes that glow brightly with radio emission. These are the Mickey Mouse ears we see with our radio telescopes. The scale of these structures is almost impossible to comprehend. Take Hercules A, for example. This radio galaxy is about 2 billion light-years away, and its radio lobes extend more than 1.5 million light-years from end to end. To put that in perspective, the distance from our Milky Way to our nearest large galactic neighbor, Andromeda, is only about 2.5 million light-years. One radio galaxy, one single galaxy's black hole activity, is creating a structure nearly as large as the space between entire galaxies. And here's something that really makes you think. These jets have been running continuously for millions of years. We know this because we can see the structure of the lobes, the way they've carved out cavities in the intergalactic medium, the history written in radio waves. The supermassive black hole at the center of these galaxies has been continuously firing these cosmic blowtorches for longer than human civilization has existed, longer than our species has walked the Earth, longer even than our genus has been around. That's persistence. Now, you might be wondering, why radio waves? What makes radio galaxies special in that particular part of the electromagnetic spectrum? It all comes down to what's happening in those jets and lobes. The particles streaming out from the black hole, primarily electrons, are traveling through magnetic fields at nearly the speed of light. And when you accelerate charged particles through magnetic fields, they emit radiation in a process called synchrotron radiation. For the speeds and field strengths we're talking about in radio galaxies, that radiation happens to fall right in the radio part of the spectrum. But here's the beautiful thing. That same physics that creates radio waves from terrestrial particle accelerators like the Large Hadron Collider is creating radio waves in these cosmic jets. It's a perfect example of how the same fundamental laws of physics operate everywhere in the universe, from the smallest laboratory experiments to the most massive cosmic structures. Nature isn't creative with physics. It just uses the same tools over and over again, just at wildly different scales. One of the most fascinating aspects of radio galaxies is how they evolve over time. These aren't static structures frozen in space. They're dynamic, living, breathing systems that change and grow. Young radio galaxies might have compact jets, barely extending beyond their host galaxy. As they age and the jets continue to pump energy into the intergalactic medium, the lobes grow larger and larger, eventually reaching those million light-year scales we talked about. But nothing lasts forever. Eventually, the black hole runs out of fuel, or the jets shut off for reasons we don't entirely understand yet. When that happens, the jets disappear relatively quickly, astronomically speaking. But the lobes? Those take much longer to fade. They slowly lose energy, their particles slow down, and they gradually dim and become invisible to our radio telescopes. These dead radio galaxies are ghosts of former glory, testament to a time when their central black hole was feasting voraciously. There's this incredible object called Centaurus A, and it's one of the closest radio galaxies to us, only about 12 million light-years away. That's basically in our cosmic backyard. With a modest telescope, you can actually see Centaurus A as an elliptical galaxy with this striking dark dust lane cutting across its middle. But point a radio telescope at it, and suddenly you see these massive lobes extending far beyond the visible galaxy, the unmistakable signature of an active galactic nucleus powered by a supermassive black hole. What makes Centaurus so special is that we can study it in exquisite detail precisely because it's so close. We've discovered that it's not just a simple double-lobed radio galaxy. It has multiple sets of lobes, suggesting that its central black hole has had several episodes of activity over its lifetime, turning on and off like a cosmic light switch across millions of years. It's like reading a history book written in radio waves, each chapter telling us about a different epoch of feeding and jet production. And here's something that connects to the bigger picture of how galaxies evolve. Radio galaxies aren't random. They tend to be associated with giant elliptical galaxies, the massive, bloated structures we find at the centers of galaxy clusters. These galaxies got that way through cosmic violence, through the merger and collision of smaller galaxies over billions of years. And galaxy mergers? They're fantastic at funneling gas into the central regions of galaxies, right down to where those supermassive black holes are waiting. So in a very real sense, radio galaxies are signposts of cosmic history. When we see an active radio galaxy, we're often seeing the aftermath of a galaxy collision that happened hundreds of millions of years ago. We're seeing the consequences of cosmic evolution written in jets of plasma and lobes of synchrotron radiation. Every radio galaxy is a story about growth, violence, and transformation on a galactic scale. Let's talk about one of the most extreme examples we've ever found, 3C236. This radio galaxy holds the record for the largest known structure associated with a single galaxy. From end to end, its radio lobes span an absolutely staggering 15 million light-years. Think about that, 15 million light-years. That's roughly the distance across a small cluster of galaxies. One galaxy's black hole created a structure so large it could contain hundreds of galaxies the size of the Milky Way. The energy required to create and maintain such a structure is almost beyond comprehension. We're talking about the equivalent of converting millions of solar masses directly into energy over the lifetime of the jets. That's more energy than our sun will produce in its entire 10 billion-year lifetime, and it's being pumped out continuously for millions of years. The supermassive black hole at the center of 3C236 is one of the most powerful engines in the observable universe. But radio galaxies aren't just cosmic curiosities. They play a crucial role in something called AGN feedback, which stands for active galactic nucleus feedback, and it's one of the most important processes in modern astrophysics. Here's the idea: those jets we've been talking about, they don't just create pretty radio lobes in the intergalactic medium. They inject enormous amounts of energy into the gas in and around their host galaxies. That energy heats the gas, sometimes to tens of millions of degrees, making it too hot to collapse and form new stars. In essence, the radio galaxy's black hole is regulating star formation in its host galaxy. It's like a cosmic thermostat, preventing the galaxy from turning all its gas into stars too quickly. Without this feedback, our theoretical models predict that galaxies should be much more massive and much bluer, filled with young stars, than what we actually observe. Radio galaxies, and active galactic nuclei in general, are a critical piece of the puzzle in understanding why galaxies look the way they do. There's this beautiful example in the Perseus cluster, a massive cluster of galaxies about 240 million light-years away. At its center sits a giant elliptical galaxy with an active supermassive black hole, and that black hole is blowing bubbles. Actual bubbles of radio-emitting plasma in the hot gas that fills the cluster. These bubbles are hundreds of thousands of light years across, and they're preventing the cluster's gas from cooling down and forming new stars in the central galaxy. We can literally see the black hole's influence written in the structure of the cluster itself. Now, I want to talk about something that demonstrates just how strange these objects really are: superluminal motion. Here's what happens. When a jet is pointed almost directly at us at just a slight angle, something weird occurs. Because the jet is moving at nearly the speed of light, and it's pointed toward us, the light from the far end of the jet doesn't have much farther to travel to reach us than the light from the near end. This creates an optical illusion where features in the jet appear to be moving faster than light, sometimes several times the speed of light. Now, before you call up your local physics department to report a violation of special relativity, let me assure you, nothing is actually traveling faster than light. It's a geometric effect, a trick of perspective combined with the extreme velocities involved. But the first time astronomers observed this in radio galaxies, in sources like 3C273, it caused quite a stir. It was direct, observable evidence that these jets really were traveling at a significant fraction of the speed of light. We weren't just theorizing about relativistic jets anymore. We were watching them happen in real time, or at least as real time as you can get when observing objects millions or billions of light years away. Speaking of 3C273, let's talk about quasars for a moment, because they're intimately related to radio galaxies. Quasars, or quasi-stellar objects, were discovered in the 1960s as incredibly bright, star-like points of light that were emitting powerful radio waves. When astronomers measured their distances using spectroscopy, they were shocked. These weren't stars at all. They were among the most distant and luminous objects in the universe, single sources outshining entire galaxies. We now know that quasars are just another face of the same phenomenon we see in radio galaxies. They're supermassive black holes actively feeding, seen from a different angle. If we happen to be looking almost directly down one of the jets, we see a quasar impossibly bright and energetic. If we're looking from the side, we see a radio galaxy with its characteristic lobes. It's all the same physics, just viewed from different perspectives. This is what we call the unified model of active galactic nuclei, and it's one of the great successes of modern astronomy. There's something profound about the fact that something as violent and energetic as a radio galaxy can also be responsible for shaping the evolution of its host galaxy in such a delicate way. It's like the universe has this built-in balancing mechanism. Black holes grow by consuming matter, but in the process of consuming matter, they generate so much energy that they limit how much matter can actually reach them. It's a self-regulating system, playing out across millions of years and millions of light years. Let me tell you about Cygnus A, because it's one of the most studied radio galaxies in the sky and it beautifully illustrates many of the concepts we've been discussing. Discovered in 1939, Cygnus A was one of the first radio sources ever identified, and it remains one of the brightest radio sources in the sky, even though it's about 600 million light years away. That tells you something about how incredibly powerful it is. When astronomers first got detailed radio images of Cygnus A in the 1980s using the Very Large Array in New Mexico, they saw something spectacular. The classic double-lobe structure, yes, but also intricate details in the jets connecting the central galaxy to the lobes. They could see hotspots where the jets were slamming into the intergalactic medium, like cosmic fire hoses hitting a wall. They could see the structure of the lobes themselves, twisted and contorted by their interaction with the surrounding environment. And when they looked at Cygnus A with X-ray telescopes, they found something even more interesting. The lobes were surrounded by a cocoon of hot, X-ray emitting gas, shock-heated by the expansion of the radio lobes into the surrounding medium. Here was direct evidence of that AGN feedback process we talked about. The radio galaxy wasn't just creating pretty structures. It was actively heating and disrupting the gas around it, affecting the ability of its host galaxy and nearby galaxies to form stars. Let's zoom out for a moment and think about what radio galaxies tell us about the history of the universe. We can observe radio galaxies at all different distances, which means we can see them at different times in cosmic history. Remember, because light travels at a finite speed, looking at distant objects means looking back in time. A galaxy 1 billion light-years away is being seen as it was 1 billion years ago. What we've found is fascinating. Radio galaxies were more common in the past than they are today. The peak of radio galaxy activity happened when the universe was roughly 1/4 to 1/2 its current age, around 7 to 10 billion years ago. This makes sense. That was the era of peak galaxy merger activity, when the universe was smaller and galaxies were more likely to run into each other. Those mergers funneled gas into galactic centers, feeding supermassive black holes and triggering radio jet activity. Today, the universe has expanded, galaxies are more spread out, and galaxy mergers are less common. Most supermassive black holes are dormant or only weakly active. But back in that earlier era, the universe was a much more violent place, filled with colliding galaxies and active radio galaxies lighting up the cosmos with their powerful jets. In a sense, we're living in a relatively quiet period of cosmic history. Now, here's something that really demonstrates the cutting edge of research in this field. Scientists are now discovering what they call giant radio galaxies, or GRGs. These are radio galaxies with lobes extending more than 2.3 million light-years from end to end. They're not just big, they're enormous even by the standards of radio galaxies. And here's the mystery. We're not entirely sure why some radio galaxies become giants while others don't. Is it because their jets have been running for longer? Is it because they exist in lower density environments where there's less resistance to the expanding lobes? Is it something about the black hole itself, or the way it's feeding? These are active areas of research, and the answers will tell us important things about the life cycle of radio galaxies and how they interact with their environments. The coolest part about studying these giant radio galaxies is that they're excellent probes of the intergalactic medium. As their lobes expand, they're sampling the properties of the gas between galaxies across enormous volumes of space. By studying the structure and brightness of the lobes, we can learn about the density, temperature, and magnetic field strength of this otherwise nearly invisible intergalactic gas. Let's talk about the tools we use to study radio galaxies, because the technology here is genuinely impressive. Modern radio telescopes don't look like the giant satellite dishes you might be imagining. Well, some of them do, but the most powerful ones are arrays of many smaller dishes or antennas spread out across large distances, all working together as a single giant telescope. The Very Large Array in New Mexico, for example, consists of 27 individual antennas, each 25 meters in diameter, arranged in a Y-shape that can extend up to 36 kilometers across. By combining the signals from all 27 antennas using a technique called interferometry, astronomers can achieve the angular resolution of a single telescope 36 kilometers in diameter. That's the equivalent of being able to read a newspaper in Los Angeles from New York City. And it gets even better. There's a technique called Very Long Baseline Interferometry, or VLBI, where radio telescopes across entire continents or even across the Earth work together. The Event Horizon Telescope, which captured that famous image of the black hole shadow in the galaxy M87, is a VLBI array. And M87? That's a radio galaxy. The jets and lobes from M87 have been studied for decades, and now we've even imaged the immediate vicinity of its supermassive black hole, the engine that powers the entire system. That image of the M87 black hole is genuinely one of the most important images in the history of science. We're seeing the shadow of a black hole cast against the glow of superheated matter in the accretion disk in a galaxy 55 million light-years away. We're probing the region where Einstein's general relativity is at its most extreme, where space and time are warped almost beyond recognition. And this is the same galaxy that's launching jets millions of light-years into space. It's the same phenomenon we see in radio galaxies across the universe, and now we've imaged the very engine that powers it all. The future of radio galaxy research is incredibly exciting. We're building new, more powerful radio telescopes that will let us see fainter and more distant radio galaxies than ever before. The Square Kilometre Array, currently under construction in South Africa and Australia, will be the most sensitive radio telescope ever built, with a total collecting area of 1 square kilometer. That's equivalent to 140 football fields worth of radio collecting surface. With instruments like the SKA, we'll be able to study radio galaxies in the very early universe, perhaps even detecting the first radio galaxies that formed when the cosmos was less than 1 billion years old. We'll be able to study the detailed structure of jets and lobes in unprecedented detail, watching how they evolve and interact with their surroundings. We'll be able to conduct massive surveys, finding and cataloging hundreds of thousands of radio galaxies, giving us a complete census of these objects across cosmic history. But beyond just studying radio galaxies themselves, these observations will tell us about the evolution of galaxies, the growth of supermassive black holes, the properties of the intergalactic medium, and even cosmology itself. Radio galaxies can be used as cosmic yardsticks, helping us measure distances across the universe. They can tell us about the large-scale structure of the cosmos, how galaxies are distributed, and how they cluster together. There's also the question of how supermassive black holes got so massive in the first place. We now know that even galaxies in the very early universe, when the cosmos was less than 1 billion years old, harbor supermassive black holes containing billions of solar masses. How did they get so big so fast? That's one of the major mysteries in modern astrophysics. Did they form from the collapse of massive clouds of primordial gas? Did they grow from smaller black holes through mergers and accretion? The answer probably involves some combination of both, and studying radio galaxies across cosmic time will help us figure it out. Here's something that brings it all back to Earth. Quite literally, every technological device that receives radio waves, from your car's FM radio to your Wi-Fi router to the GPS satellite navigation system, relies on the same principles of electromagnetic radiation that we use to study radio galaxies. The difference is scale. Your car radio is detecting radio waves with wavelengths of a few meters, transmitted from a tower a few dozen kilometers away, carrying maybe a few thousand watts of power. A radio telescope detecting a distant radio galaxy is picking up radio waves with similar wavelengths, but they've traveled billions of light years across space, and they originated from a system pumping out more power than 1 billion suns. It's a testament to both the power of radio galaxies and the sensitivity of our instruments that we can detect them at all. The amount of radio wave energy reaching Earth from even the brightest radio galaxy is absolutely minuscule. We're talking about power levels in the billionths of a billionth of a watt per square meter. And yet, we can not only detect these signals, but we can study them in exquisite detail, mapping out structures millions of light years across with precision that would have seemed like magic just a few decades ago. Every time we discover something new about radio galaxies, we're learning something fundamental about how the universe works. We're seeing physics in its most extreme form, playing out on scales both enormous and tiny. We're watching supermassive black holes, objects where space and time literally end, somehow generating jets that travel millions of light years and affect entire galaxy clusters. We're seeing the delicate balance between destruction and creation, between gravity that pulls everything together and energy that blows everything apart. And perhaps most remarkably, we're doing all of this with telescopes here on Earth, or in Earth orbit, looking up at the sky and collecting ancient photons that have been traveling through space for millions or billions of years just to tell us their story. We're listening to radio waves, invisible to our eyes, inaudible to our ears, but rich with information about the most spectacular phenomena in the cosmos. The next time you think about black holes, don't just think about them as cosmic vacuum cleaners, swallowing everything around them. Think about them as the engines of radio galaxies, as cosmic particle accelerators that create structures millions of light years across, as the thermostats that regulate how galaxies grow and evolve. Think about them as one of the universe's most spectacular demonstrations that even in the darkest, most destructive forces in nature, there's beauty, there's complexity, and there's something fundamentally creative. Radio galaxies remind us that the universe is far stranger and more wonderful than our everyday experience suggests. They show us that reality operates on scales both far larger and far smaller than we can directly perceive, that the laws of physics we discover in laboratories here on Earth apply across billions of light years of space and billions of years of time. They demonstrate that we live in a dynamic, evolving universe, not a static cosmos frozen in time. And they inspire us to keep looking, keep questioning, keep probing the edges of our knowledge. Because for every question we answer about radio galaxies, we discover two new mysteries. How do the jets maintain their collimation across such vast distances? What triggers the transition from radio loud to radio quiet activity? How do magnetic fields get organized and amplified in the extreme environment near a black hole? These aren't just academic questions. They're about understanding the fundamental workings of the universe. So the next time someone tells you that astronomy is just about looking at pretty pictures of stars and galaxies, tell them about radio galaxies. Tell them about black holes launching jets at nearly the speed of light. Tell them about structures millions of light years across, about energies that dwarf anything we can imagine, about processes that have been running continuously for longer than human civilization has existed. Tell them about how we can't see any of this with our eyes, but we've built instruments that can, and those instruments have revealed a universe far more spectacular than anyone could have imagined just a century ago. Radio galaxies are out there right now, beaming their signals across the cosmos. They've been doing it for millions of years, and they'll keep doing it for millions more. They're shouting into the void, and we're here, listening, learning, and marveling at the sheer audacity of the universe to create something so magnificent. They're reminding us that we're part of this cosmos, governed by the same physics, made of the same atoms that were forged in the hearts of stars and scattered across space by supernovae billions of years ago. In the end, studying radio galaxies is about more than just understanding these particular objects. It's about understanding our place in the universe, about recognizing that we live in a cosmos of almost incomprehensible scale and complexity, but also one that we can understand, at least in part, through careful observation, clever thinking, and powerful instruments. It's about the human drive to explore, to question, to push the boundaries of what we know. Every radio galaxy we study is a window into the workings of the cosmos. Every jet we map, every lobe we analyze, every black hole we probe adds another piece to the puzzle of how the universe operates. And that puzzle, vast and intricate as it is something we're actually solving one observation at a time, one discovery at a time, one moment of insight at a time. The universe is speaking to us in radio waves, and through radio galaxies, it's telling us stories of power and beauty on the grandest scales imaginable. All we have to do is listen. But let's dig deeper into something that'll really make you appreciate the bizarreness of these objects. You know how I mentioned that jets can travel at 99.9% the speed of light? Well, let's talk about what that actually means for the physics happening inside those jets. When particles move that fast, relativistic effects become absolutely critical. Mass increases, time dilates, lengths contract in the direction of motion. The universe itself starts behaving in ways that seem utterly counterintuitive to our everyday experience. Inside these jets, you've got electrons and protons being accelerated to energies that make the Large Hadron Collider look like a child's toy. Individual particles can carry energies equivalent to a fastball thrown by a major league pitcher, except this energy is contained in something a trillion times smaller than a baseball. These are what we call ultra-relativistic particles, and they're careening through space in tightly focused beams that can extend for millions of light years without dispersing significantly. How do the jets stay so focused? That's actually one of the most fascinating puzzles in astrophysics. You'd think that a beam of charged particles, all pushing against each other with electromagnetic forces, would spread out immediately, like smoke from a chimney or water from a garden hose. But these cosmic jets maintain their collimation across distances that are mind-boggling. The secret lies in magnetic fields. The jets are threaded with powerful magnetic fields that act like invisible cables, constraining the charged particles and keeping them moving in the same direction. These aren't just any magnetic fields either. We're talking about field strengths that can be millions of times stronger than Earth's magnetic field, twisted and amplified by the rotation of the accretion disk and the black hole itself. The magnetic field lines are dragged along with the outflowing material, creating a self-confining system where the field helps hold the jet together, and the jet helps maintain the field structure. There's this beautiful concept in plasma physics called the Poynting flux, and it's crucial for understanding how these jets work. Basically, electromagnetic fields themselves can carry energy and momentum, not just the particles. In the inner parts of radio galaxy jets, especially close to the black hole, a significant fraction of the energy might actually be carried by the magnetic fields themselves rather than the kinetic energy of the particles. It's only as the jet travels outward that this electromagnetic energy gets converted into the kinetic energy of particles. Think about that for a moment. The black hole is essentially creating a river of electromagnetic energy, flowing outward at nearly the speed of light, that gradually transforms into a river of high-speed particles. It's like the universe has found a way to turn pure field energy into matter in motion, all while maintaining a coherent structure across distances that span significant fractions of the observable universe. Now, here's where things get even weirder. Remember how I mentioned that some jets are pointed almost directly at us? These are called blazars, and they're among the most violently variable objects in the sky. A blazar can change its brightness by factors of 2 or more in a matter of hours or days. That's insane when you consider that we're talking about objects billions of light years away. The reason for this variability is what we call Doppler boosting. When a jet is pointed nearly at us, not only does it appear brighter due to relativistic effects, but any changes in the jet, any fluctuations in the particle density or magnetic field strength, get compressed in time from our perspective. An event that takes a month to occur in the jet's reference frame might appear to happen in just a few days or hours from our viewpoint. It's like watching a cosmic movie on fast forward. Some blazars have been observed to flare up to more than 100 times their normal brightness in less than a day. To put that in perspective, imagine if the entire Milky Way galaxy suddenly became 100 times brighter overnight. That's the kind of dramatic variability we're seeing in the cores of these radio galaxies when they're oriented just right. And the fact that this happens so quickly tells us something profound. The region producing this emission must be incredibly compact, smaller than our solar system despite containing a black hole millions or billions of times more massive than the Sun. Let's talk about particle acceleration for a minute, because this is where radio galaxies really show off their cosmic prowess. The particles in these jets aren't just moving fast. Many of them are cosmic rays, the most energetic particles we've ever detected. Some cosmic rays hit Earth with energies exceeding 10 to the 20th electron volts. That's about the kinetic energy of a tennis ball served by a professional player, except concentrated in a single subatomic particle. For decades, we've been trying to figure out where these ultra-high-energy cosmic rays come from. Supernovae can accelerate particles to high energies, but probably not high enough to explain the most energetic cosmic rays. Pulsars, rotating neutron stars, might contribute. But radio galaxy jets? They're excellent candidates for accelerating particles to these extreme energies. The mechanism is something called Fermi acceleration, named after the physicist Enrico Fermi who first proposed it. Imagine a particle bouncing back and forth between moving magnetic field structures, like a ball bouncing between the front and back walls of an accelerating train. Each bounce adds energy to the particle. In the turbulent, magnetic field-rich environment of a radio galaxy jet, particles can undergo countless such interactions, each time gaining a little more energy, until eventually they reach truly astronomical energies. These accelerated particles, when they eventually escape the jet and travel through the galaxy and intergalactic space, become the cosmic rays that occasionally strike Earth's atmosphere. In a very real sense, radio galaxies might be partly responsible for the constant drizzle of high-energy particles raining down on our planet from space. Some of the particles hitting our atmosphere right now might have been accelerated in a radio galaxy jet billions of light years away, traveling across most of the observable universe before arriving here. Now let's talk about something that connects radio galaxies to one of the deepest questions in cosmology: the nature of dark matter and dark energy. Radio galaxies can actually help us probe these mysterious components of the universe. Here's how. The giant radiolobes we've been discussing are affected by the gravity of everything around them, including dark matter. By carefully studying the shapes and sizes of radiolobes, how they're bent and distorted, we can learn about the distribution of mass in galaxy clusters, including the dark matter that makes up about 85% of all matter in the universe. Radiolobes act like enormous tracers, illuminating the otherwise invisible gravitational landscape of the cosmos. There's also gravitational lensing. When a radiogalaxy happens to lie behind a massive foreground object like a galaxy cluster, the gravity of that cluster bends the light, or in this case the radio waves, from the background radiogalaxy. This creates distorted, sometimes multiple images of the radiolobes. By analyzing these distortions, we can map out the mass distribution in the foreground cluster with incredible precision, revealing not just where the visible matter is, but where the dark matter is concentrated. Some of the most beautiful examples come from systems like the cosmic horseshoe, where gravitational lensing creates nearly complete rings of radio emission around foreground galaxies. These Einstein rings, named after the physicist who predicted them, are natural cosmic laboratories for studying both the properties of radiogalaxies and the distribution of dark matter in the lensing galaxies. And here's a connection to dark energy, the mysterious force accelerating the expansion of the universe. Radiogalaxies at different distances, and therefore different cosmic epochs, can be used as what astronomers call standard rulers. By comparing their physical sizes to their apparent angular sizes on the sky, we can measure how the universe has expanded over cosmic time. This gives us information about the expansion history of the universe, which in turn tells us about the properties of dark energy. Let me share something about the diversity of radiogalaxies that often gets overlooked. Not all radiogalaxies are created equal. There are two main classes, which we call Fanneroff-Rayleigh Type 1 and Type 2, or just FRI and FR2 for short. This classification, proposed by British astronomers Bernie Fanneroff and Julia Riley in 1974, is based on the distribution of radio brightness in the lobes. FRI radiogalaxies are generally less luminous, and their brightness peaks close to the central galaxy, fading as you move outward along the jets. They're like cosmic flashlights, brightest at the source. FR2 radiogalaxies, on the other hand, have their brightness concentrated in hotspots at the far ends of the lobes, where the jets slam into the intergalactic medium. They're like cosmic floodlights, brightest at the edges. This isn't just a cosmetic difference. It tells us something fundamental about the physics of jet propagation. FRI jets probably start out just as powerful as FR2 jets, but they lose their collimation more quickly. They transition from being narrow, focused beams to being broader, more turbulent flows while still relatively close to the central galaxy. FR2 jets maintain their focus all the way to the end, where they terminate in those bright hotspots. Why do some radiogalaxies become FRI while others become FR2? It seems to depend on a combination of factors: the power of the jets themselves, the density of the environment they're moving through, and possibly the speed at which the jets are launched. More powerful jets moving through lower density environments tend to be FR2. Less powerful jets in denser environments tend to be FRI. But there are exceptions and edge cases that keep researchers busy trying to refine our understanding. Here's something truly mind-bending: bent double radiogalaxies, also called wide-angle tails or X-shaped radiogalaxies. These are radiogalaxies where the jets aren't pointing in opposite directions from the nucleus. Instead, they're bent, sometimes by more than 90 degrees, creating U-shaped or even X-shaped structures in the sky. What causes this? Sometimes it's the motion of the galaxy through the intergalactic medium. If a galaxy is moving through the hot gas in a galaxy cluster at hundreds or thousands of kilometers per second, the ram pressure of that gas can blow the jets backward, like smoke from a moving chimney. These are called head-tail radiogalaxies, and they're excellent tracers of galaxy motion in clusters. But X-shaped radiogalaxies are different. They have two pairs of lobes, oriented at large angles to each other. One leading explanation is that we're seeing the aftermath of a black hole merger. When two galaxies collide and their central black holes eventually merge, the spin axis of the merged black hole might be different from the spin axis of the original black holes. The result? The direction of jet production changes, creating a new pair of lobes at a different angle from the old pair. We're literally seeing the fossil record of a black hole merger written in radio emission millions of light years across. Let's talk about the immediate environment around the black hole, the place where it all begins. This region, just outside the event horizon, is called the ergosphere in rotating black holes, and it's where some truly wild physics happens. The rotation of the black hole literally drags space-time around with it, a phenomenon called frame dragging. Anything in this region, including magnetic field lines, is forced to rotate along with the black hole whether it wants to or not. There's a mechanism called the Blandford-Znajek process, named after the astrophysicists Roger Blandford and Roman Znajek, that explains how rotating black holes can power jets. The basic idea is that magnetic field lines threading through the ergosphere get twisted up by the black hole's rotation. This creates enormous electrical voltages, which accelerate charged particles away from the black hole. The black hole's rotational energy is being tapped and converted into jet power. This is profound. It means that the black hole isn't just powering jets through the gravitational energy of infalling matter. It's also extracting energy from its own rotation, from the spin-angular momentum of the black hole itself. Over millions of years of jet production, a black hole could theoretically spin down, losing rotational energy as it powers these enormous cosmic outflows. The black hole is literally giving up a piece of itself to create the jets we observe. Now, contrast this with another mechanism, the Blandford-Payne process, which extracts energy from the accretion disk rather than from the black hole itself. In this scenario, magnetic field lines anchored in the disk get twisted by the disk's rotation, launching material outward. Both mechanisms are probably operating simultaneously in real radio galaxies, with the relative importance of each depending on the details of the black hole spin and the accretion flow. Let me tell you about one of the most spectacular discoveries in recent years: giant cavities blown in the hot gas of galaxy clusters by radio galaxy jets. We see these with X-ray telescopes like Chandra and XMM Newton. The jets punch enormous bubbles into the cluster gas, sometimes hundreds of thousands of light years across, and these bubbles show up as dark regions in X-ray images because they've been evacuated of hot gas. But here's where it gets interesting. These bubbles don't just sit there. They're buoyant. The hot gas inside the bubbles is less dense than the surrounding cluster gas, so they rise like hot air balloons toward the outskirts of the cluster. As they rise, they stir up the cluster gas, mixing it, preventing it from cooling and flowing back into the central galaxy. It's a cosmic version of stirring a pot of soup to keep it from settling and burning on the bottom. The amount of energy required to blow these bubbles is staggering. In some clusters, like the Perseus cluster I mentioned earlier, the total energy in the bubbles is equivalent to about 10 to the 61st ergs. That's a 1 followed by 61 zeros. To put that in perspective, it's roughly equal to the total energy output of our Sun over its entire 10 billion-year lifetime, multiplied by a billion. And this energy has been deposited into the cluster gas repeatedly over multiple episodes of jet activity spanning hundreds of millions of years. This is the AGN feedback process in action, and it's one of the most important discoveries in modern astrophysics. Without it, the hot gas in galaxy clusters would cool down, fall into the central galaxy, and trigger enormous bursts of star formation. The central galaxy would be vastly more massive than what we observe. The fact that this doesn't happen, that central cluster galaxies are actually relatively quiescent despite sitting in huge reservoirs of gas, is directly due to the heating provided by radio galaxy jets. Here's something that connects to chemistry and the origin of elements. The jets don't just heat gas. They also transport material. Gas from the immediate vicinity of the supermassive black hole, which has been enriched with heavy elements from supernovae in the central galaxy, gets carried outward by the jets and deposited into the intergalactic medium. These jets are cosmic fountains, enriching the gas between galaxies with elements like carbon, oxygen, iron, and all the other building blocks of planets and life. When the next generation of stars forms, perhaps in smaller galaxies falling into the cluster or in gas clouds far from any galaxy, they'll incorporate these heavy elements. In a very real sense, radio galaxy jets are participating in the cosmic cycle of matter, helping to spread the products of stellar nucleosynthesis across vast regions of space. Some of the atoms in your body, the iron in your blood, or the calcium in your bones might have once been part of a jet from a radio galaxy billions of years ago. Let's talk about time variability in more detail. Radio galaxies aren't static sculptures frozen in space. They're dynamic, evolving systems that change on every timescale we can observe. On the shortest timescales, hours to days, we see flickering and flaring in the cores, probably due to instabilities in the accretion disk or changes in the jet launching region. On timescales of years to decades, we can actually see features moving outward along the jets in some nearby radio galaxies, direct evidence of the flow of material away from the black hole. On timescales of millions of years, the overall morphology changes. Young radio galaxies have small, bright lobes close to the nucleus. As they age, the lobes expand, becoming larger and fainter. Eventually, the jets may shut off entirely, leaving behind fading relic lobes that slowly mix with the intergalactic medium and disappear. And then, perhaps after another galaxy merger brings fresh fuel to the central black hole, the jets can turn back on, creating a new generation of lobes. This gives radio galaxies a life cycle almost like living organisms. Birth, when the black hole starts feeding and launches jets. Youth, when the jets are powerful and the lobes are bright and compact. Maturity, when the lobes have reached their maximum extent and the jets may be declining in power. And death, when the jets shut off and the lobes fade away. Except death isn't necessarily permanent, because a new cycle can begin, creating what we call double-double or triple-double radio galaxies with multiple generations of lobes. One of the most intriguing aspects of radio galaxy research is the search for the missing link between different types of active galactic nuclei. We know that radio galaxies, quasars, Seyfert galaxies, blazars, and various other exotic objects are all fundamentally the same thing: accreting supermassive black holes. The differences we observe are largely due to viewing angle and the power of the activity. But there are gaps in our understanding. What causes a black hole to suddenly start feeding voraciously? Why do only about 10% of active galactic nuclei produce powerful radio jets, while the other 90% are radio quiet? What determines whether an active nucleus becomes radio loud or radio quiet? These questions strike at the heart of black hole physics and remain areas of active research. One hypothesis is that it's all about black hole spin. Rapidly rotating black holes might be better at launching powerful jets through the Blandford-Znajec mechanism I described earlier. If this is true, then radio galaxies might represent a special population of black holes that have built up significant spin through prolonged accretion or through specific types of mergers. But testing this hypothesis is challenging because measuring black hole spin from millions or billions of light years away isn't easy. Here's something about the connection between radio galaxies and gravitational waves. When we detect gravitational waves from merging black holes using observatories like LIGO and Virgo, we're typically observing stellar mass black holes, things between a few and a few hundred times the mass of the Sun. But supermassive black holes, the kind that power radio galaxies, also merge. And when they do, they produce gravitational waves at much lower frequencies. There's an ongoing effort to detect these low-frequency gravitational waves using pulsar timing arrays. The idea is to monitor a large number of millisecond pulsars, which are incredibly regular natural clocks, and look for correlated timing variations that would indicate a gravitational wave passing through our region of space. If successful, this will open up an entirely new window on supermassive black hole mergers, potentially letting us detect mergers happening in radio galaxies across the cosmos. The ultimate goal would be to observe a black hole merger with both electromagnetic telescopes, seeing the radio galaxy activity before and after the merger, and with gravitational wave detectors, catching the actual merger event itself. This kind of multi-messenger astronomy, combining different types of signals from the same event, is the future of the field and promises to revolutionize our understanding of how supermassive black holes grow and evolve. Now, let me tell you about some truly bizarre radio galaxies that challenge our understanding. There's an object called J1420-0545, a radio galaxy where the jets appear to be precessing, wobbling like a spinning top. Over the course of millions of years, the direction of the jets has changed, creating a spiral or corkscrew pattern in the radio emission. This might be evidence of a binary supermassive black hole system, where two black holes are orbiting each other, and their gravitational interaction causes the accretion disk and jets to precess. Then there's 3C75, a system in the Abell 400 galaxy cluster where we're seeing two radio galaxies in the process of merging. Each galaxy has its own supermassive black hole producing jets, and we can see both sets of jets in the same system, bent and distorted by the galaxy's orbital motion and interaction with the cluster gas. This is a preview of what will eventually happen to the Milky Way and Andromeda galaxies when they collide a few billion years from now, assuming our galactic black holes become active. There are also what we call restarted radio galaxies, where we can clearly see evidence of multiple episodes of jet activity. The signature is the presence of both old, fading lobes far from the nucleus and new, bright lobes close in. The time gap between these episodes can be millions to tens of millions of years. It's like the black hole took a break, stopped eating for a while, and then came back for seconds. What triggers these cycles of activity and quiescence? Galaxy interactions and mergers are the obvious culprits. A close encounter with another galaxy can gravitationally torque the gas in a galaxy, sending it spiraling inward toward the central black hole. But the details of how this works, the exact mechanisms that control the flow of gas from galactic scales down to the black hole's accretion disk, are still being worked out. There's this concept called the sphere of influence of a black hole. It's the region around the black hole where its gravity dominates over the gravity of the stars in the galaxy. For a supermassive black hole with 1 billion solar masses in a giant elliptical galaxy, this sphere of influence might extend for hundreds of light years. That sounds like a lot, but it's tiny compared to the size of the galaxy, which could be 100,000 light years across. So there's this enormous gulf, several orders of magnitude in scale, between the size of the galaxy where the gas starts and the black hole sphere of influence where it needs to end up. How does the gas make that journey? Angular momentum is the problem. Gas orbiting the galaxy has angular momentum, and that angular momentum prevents it from simply falling straight into the center. Something has to remove that angular momentum, and that's where the complexity comes in. Gravitational instabilities in the gas disk can help. Spiral density waves can transport angular momentum outward while allowing gas to move inward. Supernova explosions from star formation can disrupt the gas, creating turbulence that helps funnel material toward the center. And once you get close enough, the black hole's jets themselves can affect the surrounding gas, stirring it up and paradoxically both preventing some gas from falling in while helping other gas lose angular momentum and accrete. It's a delicate dance, a cosmic feedback loop where the black hole's activity regulates its own fuel supply. Too much feeding and the jets blow away the surrounding gas, cutting off the food supply. Too little feeding and the jets weaken, allowing more gas to accumulate. Over millions of years, this creates a cycle of activity and quiescence, feast and famine, that we observe as the episodic nature of radio galaxies. Let's pivot and talk about something really cutting edge, using radio galaxies to probe the epoch of reionization. This was a critical period in cosmic history, roughly 200 to 900 million years after the Big Bang, when the first stars and galaxies formed and their radiation ionized the neutral hydrogen that filled the universe. Before reionization, the universe was dark and opaque to most wavelengths of light. After reionization, it became transparent, the way we see it today. Radio waves from distant radio galaxies have to travel through this early universe to reach us. And the state of the intergalactic medium, whether it's neutral or ionized, affects these radio waves. Neutral hydrogen absorbs certain radio frequencies very efficiently. By studying the radio spectra of very distant radio galaxies, looking for signatures of this absorption, we can learn about when and how reionization happened. This is technically challenging because these ancient radio galaxies are incredibly faint, and their radio emission has been redshifted to lower frequencies by the expansion of the universe. But upcoming radio telescopes like the Square Kilometre Array are specifically designed to tackle this problem. They'll be sensitive enough to detect radio galaxies from the era of reionization and use them as backlight sources to probe the state of the intergalactic medium at different cosmic epochs. Imagine that. Using the most powerful, energetic phenomena in the universe, supermassive black holes launching jets, as cosmic flashlights to illuminate the fog of neutral hydrogen that filled the early universe. It's like using a lighthouse beam to study the properties of fog, except the lighthouse is billions of light years away and the fog is 13 billion years old. Here's another frontier: radio galaxies and cosmology. The universe is expanding, and that expansion is accelerating due to dark energy. We know this from observations of distant supernovae, from the cosmic microwave background, and from the large-scale structure of galaxies. But independent measurements are always valuable in science, and radio galaxies can provide one. There's a correlation between the radioluminosity of a radio galaxy and the physical size of its lobes. This makes sense if you think about it. More powerful jets will inflate larger lobes over their lifetime. By carefully calibrating this relationship using nearby radio galaxies where we can measure distances accurately, we can then use distant radio galaxies as cosmic distance indicators. The idea is to observe radio galaxies at various distances, measure their angular sizes on the sky, and use the known correlation between luminosity and physical size to estimate their true physical sizes. The ratio of angular size to physical size gives you the distance. Do this for many radio galaxies at many different redshifts, and you can map out the expansion history of the universe. It's an independent cross-check on other cosmological measurements, and any discrepancies could point to new physics. There's also the Alcock-Paksinski test, a geometric test of cosmology that uses the ratio of separations perpendicular to and along the line of sight. Radio galaxies in surveys can be used for this test. If our cosmological model is correct, the clustering of radio galaxies should show specific patterns. If it's wrong, the patterns will be distorted. It's a subtle effect, but with large enough surveys, it becomes detectable. Now, let's talk about something that bridges astrophysics and technology. Very long baseline interferometry in space. We have VLBI on Earth, connecting telescopes across continents to achieve incredible resolution. But why stop at Earth? There have been proposals and even some missions to put radio telescopes in space and use them as part of VLBI arrays. The Halka mission, launched by Japan in 1997, was the first space VLBI mission. It achieved angular resolutions finer than any Earth-based array at the time. Radio Astron, launched by Russia in 2011, extended these capabilities even further with a larger telescope and longer baselines. These space-based missions have studied radio galaxies and quasars with unprecedented detail, resolving structures on scales of light days or even light hours across. What do you see at these resolutions? You see the base of the jet, the region where the jet is launched from the accretion disk. You see the structure of the magnetic field in exquisite detail. You see brightness temperature, a measure of how compact and energetic the emission is, reaching values that challenge our theoretical understanding. Some sources show brightness temperatures exceeding the inverse Compton limit, which is the maximum temperature you'd expect from synchrotron radiation before other cooling processes become dominant. These extreme brightness temperatures might indicate that the emission is beamed directly at us, amplified by relativistic Doppler boosting to the point where the apparent temperature exceeds what the intrinsic physics would allow. Or they might indicate new physics, processes we haven't fully understood yet. Either way, they're pushing our understanding of plasma physics and relativistic magnetohydrodynamics to the limit. Speaking of magnetohydrodynamics, or MHD, let's dive into that for a moment. MHD is the study of electrically conducting fluids in magnetic fields, and it's absolutely crucial for understanding radio galaxy jets. The plasma in these jets is essentially a conducting fluid. threaded with magnetic fields, moving at relativistic speeds. The equations describing this situation are hideously complex, combining Einstein's special relativity, Maxwell's equations of electromagnetism, and the fluid dynamics of the plasma. Solving these equations analytically is essentially impossible for realistic situations. So astrophysicists turn to numerical simulations, running massive computer codes on supercomputers to model the behavior of jets. These simulations have become increasingly sophisticated over the years, incorporating more realistic physics, higher resolution, and larger computational volumes. Modern simulations can follow a jet from its launch near the black hole all the way out to the giant radio lobes, covering 9 orders of magnitude in scale. That's like simulating something from the size of a bacterium to the size of Earth. They show how the jet propagates through the surrounding gas, how instabilities develop and cause the jet to wobble or break up, how the magnetic field gets tangled and amplified, and how the terminal shock forms where the jet hits the intergalactic medium. These simulations have been remarkably successful at reproducing the observed structures of real radio galaxies. They've confirmed that magnetic fields are indeed crucial for jet collimation. They've shown that jets can remain stable over enormous distances if the magnetic field structure is right. And they've revealed that the detailed structure we see in radio images, things like knots of enhanced brightness along the jets or asymmetries between the two sides, often result from interactions between the jet and the surrounding medium or from instabilities within the jet itself. But simulations also show us something humbling: just how much we still don't know. The microphysics of particle acceleration in jets, for example, is still poorly understood. We know it happens, we see the energetic particles in the emission, but the exact mechanisms, the efficiency of the process, the maximum energies achievable, these are still areas of active research and debate. Let me tell you about polarization because it's one of the most powerful tools we have for studying radio galaxies. Radio waves are electromagnetic waves, and like all electromagnetic waves, they can be polarized. The electric field can oscillate in a preferred direction rather than randomly. When we observe radio galaxies with polarization-sensitive receivers, we can measure not just the brightness of the emission but also its polarization properties. And here's why that's powerful. Synchrotron radiation, the process creating the radio emission, produces naturally polarized light. The direction of polarization tells us about the orientation of the magnetic field in the emitting region. By mapping the polarization across a radio galaxy, we can map the magnetic field structure. We can see how the field is aligned with the jets, how it wraps around the lobes, how it's compressed and tangled at the shock fronts. Moreover, as polarized radio waves travel through magnetized plasma, the plane of polarization rotates in a process called Faraday rotation. The amount of rotation depends on the strength of the magnetic field along the line of sight, the density of electrons, and the frequency of the radio waves. By measuring Faraday rotation at multiple frequencies, we can probe the magnetic fields not just in the radio galaxy itself but also in any intervening material between us and the source. This has led to some fascinating discoveries. For instance, some radio galaxies show evidence of large-scale magnetic fields in the intergalactic medium, possibly left over from the early universe or generated by structure formation. Others show complex Faraday rotation patterns that reveal dense screens of magnetized material surrounding the radio source, perhaps remnants of previous episodes of activity or material from a recent galaxy merger. There's also depolarization, where regions that should be polarized appear unpolarized in our observations. This happens when the radio waves travel through turbulent magnetized plasma that scrambles the polarization. By studying depolarization, we can learn about the small-scale structure and turbulence in the interstellar and intergalactic medium, things that are otherwise very difficult to observe. Let's shift gears and talk about the connection between radio galaxies and the first supermassive black holes in the universe. Observations with telescopes like the James Webb Space Telescope are revealing supermassive black holes, millions to billions of solar masses, in galaxies when the universe was less than 1 billion years old. This is a major puzzle. How did these black holes get so massive so quickly? One possibility is that they grew from stellar mass black holes that formed from the first generation of stars. But to grow from, say, 100 solar masses to a billion solar masses in less than a billion years requires accreting matter at very high rates almost continuously. That's challenging because as black holes accrete matter, they generate radiation that pushes against the infalling material, limiting the accretion rate. This is called the Eddington limit. Another possibility is that supermassive black holes formed directly from the collapse of massive clouds of primordial gas in the early universe, creating what are called direct collapse black holes, with masses of tens of thousands to millions of solar masses right from the start. These would have a head start on growth, making it easier to reach billions of solar masses within a billion years. Radio observations of these early black holes can help distinguish between these scenarios. If early black holes are frequently producing radio jets and radio galaxies, that tells us something about their accretion states and spin. If we see evidence for particularly powerful jets or unusual jet properties in the very early universe, that might favor certain formation scenarios over others. The challenge is that radio galaxies from the very early universe are among the faintest and most difficult objects to detect. But with next-generation radio telescopes, we're on the verge of a breakthrough. Within the next decade, we expect to detect the first radio galaxies from the epoch of reionization, from when the universe was only a few 100 million years old. These observations will be crucial for understanding the origin and early growth of supermassive black holes. Here's something about the multi-wavelength nature of radio galaxies that's important to emphasize. While they're called radio galaxies because they were discovered through their radio emission, they actually emit across the entire electromagnetic spectrum. The accretion disk around the black hole emits primarily in ultraviolet and X-rays. The broadline region, if present, emits optical and UV light. The jets emit radio waves from synchrotron radiation, but they can also emit infrared, optical, X-rays, and even gamma rays through various processes. In particular, many radio galaxies are also gamma ray sources, detected by satellites like the Fermi Gamma Ray Space Telescope. The gamma rays are probably produced through inverse Compton scattering, where the high-energy electrons in the jet collide with lower-energy photons and boost them up to gamma ray energies. Studying radio galaxies in gamma rays tells us about the most energetic particles in the jets and the radiation fields they're interacting with. There are even reports of neutrinos, ghost-like particles that barely interact with matter, being detected from the directions of some blazars and radio galaxies. Neutrinos would be produced when the ultra-high-energy protons in jets collide with photons or other material, creating pions that then decay into neutrinos. Confirming radio galaxies as neutrino sources would be a major breakthrough, definitively proving that jets accelerate protons to extreme energies, not just electrons. This multi-messenger approach, studying radio galaxies with every possible type of observation, from radio waves to gamma rays to neutrinos to potentially gravitational waves, is painting an incredibly rich picture of these objects. Each wavelength, each type of particle, reveals a different aspect of the physics. Radio waves show us the large-scale structure and magnetic fields. X-rays reveal the hot spots and the accretion disk. Gamma rays probe the highest energy processes. Neutrinos would confirm hadronic acceleration. Together, they provide a complete view. Now, let me tell you about the role of citizen science in radio galaxy research. Professional astronomers can't possibly examine every radio source in large survey data by eye. But the human brain is still better than computer algorithms at recognizing complex patterns and unusual structures. So there are projects like Radio Galaxy Zoo where volunteers from the public can help classify radio galaxies, matching radio sources with their host galaxies and identifying unusual objects. Citizen scientists through Radio Galaxy Zoo have discovered some truly bizarre objects. Odd radio circles, or ORCs, were first spotted by volunteers. Nearly perfect circular rings of radio emission with no optical counterpart. We're still not entirely sure what they are. They might be blast waves from enormous explosions, or perhaps a new type of radio remnant from an unusual class of radio galaxy, or something else entirely. The fact that these were discovered by citizen scientists highlights the value of having many eyes looking at the data. There have been hundreds of scientific papers published using data from citizen science projects related to radio astronomy. This is a real partnership between professional scientists and the public, and it's accelerating the pace of discovery. Anyone with an internet connection can contribute to advancing our understanding of the universe. That's pretty remarkable. Let's talk about something more philosophical for a moment. Radio galaxies are teaching us about the nature of time and causality on cosmic scales. When we observe a radio galaxy a billion light-years away, we're seeing it as it was a billion years ago. The jets we observe are responding to conditions near the black hole from a billion years in the past. Any changes we see happen over timescales of thousands to millions of years from the perspective of the source, but compressed or extended by cosmological time dilation depending on the source's distance. Moreover, the lobes we observe are causally disconnected from the black hole in a certain sense. Light, and therefore information, travels at a finite speed. The radiation we see from the far end of a lobe left there hundreds of thousands of years ago from the perspective of the radio galaxy. Changes happening at the black hole today won't affect those distant lobes for hundreds of thousands of years. Yet the whole system maintains a remarkable coherence, with jets staying pointed in the same direction and maintaining their power output over these vast timescales. This tells us something profound about the stability of accretion disks and black hole spin axes. For a radio galaxy to maintain jets in the same direction for millions of years, the black hole's spin axis must be stable, not wobbling or precessing significantly. This in turn constrains how black holes accrete matter and how they respond to perturbations from their environment. There's also the question of coincidences and fine-tuning in the universe. The fact that supermassive black holes exist, that they can accrete matter efficiently enough to power jets, that magnetic fields naturally arise and get amplified to the right strengths, that the intergalactic medium has just the right density to create visible lobes, all of this seems almost too convenient. Is there something special about our universe that allows radio galaxies to exist? Or would they form in any universe with the same basic laws of physics? This gets at deep questions in cosmology and philosophy about the nature of physical laws and whether our universe is in some sense special or typical. Radio galaxies, by existing and having the properties they do, provide data points in this cosmic parameter space. They're natural experiments in extreme physics, testing what happens when you push gravity, electromagnetism, and matter to their limits. One thing that's become increasingly clear is that supermassive black holes and their host galaxies co-evolve. There's a tight correlation between black hole mass and various properties of the host galaxy, like the mass of the central bulge or the velocity dispersion of stars. This suggests that black hole growth and galaxy growth are intimately linked, regulating each other through feedback processes. Radio galaxies are a key part of this story. The jets provide one of the most powerful feedback mechanisms we know of, capable of affecting star formation and gas cooling across an entire galaxy or even a galaxy cluster. They're not just passengers in galactic evolution, they're active drivers. Understanding how and when galaxies produce radio jets, how those jets affect their surroundings, and how that feedback influences subsequent galaxy and black hole growth is one of the central challenges in modern astrophysics. There's emerging evidence that the orientation of a galaxy's jets might be influenced by the large-scale structure of the universe. Some studies have found that radio galaxy jets tend to align with the filaments of the cosmic web, the large-scale structure formed by dark matter and galaxies. If true, this would indicate a connection between the smallest scales, the black hole and its immediate surroundings, and the largest scales, the structure of the universe itself. How could such a connection arise? Probably through the way galaxies form and accrete gas. Galaxies in filaments tend to accrete matter along the filament direction. This matter brings angular momentum with it, and that angular momentum might preferentially align the accretion disk and hence the jets. It's speculative and the evidence is still being debated, but it's a tantalizing possibility that there's an alignment between structure on scales of millions of light years and structure on scales of light days. Let me share something about observational challenges. Detecting and studying radio galaxies isn't easy. For one thing, radio telescopes are fundamentally different from optical telescopes. They're measuring incredibly faint signals, often just a few photons per second per square meter of collecting area. And the images they produce aren't really images in the way we think of them. They're reconstructed from interferometric measurements, combining signals from multiple antennas with sophisticated algorithms. This reconstruction process, called synthesis imaging, is mathematically complex and computationally intensive. It requires correcting for effects like the Earth's rotation changing the orientation of the telescopes relative to the source, the ionosphere bending and delaying radio waves, and instrumental effects in the receivers and electronics. Modern radio interferometers produce petabytes of raw data that must be processed with supercomputers to create usable images. And even then, what you see depends on the observing frequency, the resolution of your telescope array, and the sensitivity of your receivers. A radio galaxy observed at low frequencies might show enormous diffuse lobes. The same object observed at high frequencies might show only the compact core and the brightest parts of the jets. To fully understand a radio galaxy, you need observations across a wide range of frequencies and resolutions, building up a complete picture piece by piece. There's also the challenge of variability. Some radio galaxies, particularly blazars viewed nearly along the jet axis, can change significantly over timescales of days or weeks. This means you can't just take a single observation and assume it's representative. You need monitoring campaigns, repeated observations over months or years, to understand the source's behavior. This requires substantial telescope time, and there's always competition for access to the world's premier radio facilities. Despite these challenges, the field has made enormous progress. Compare a radio image from the 1960s, grainy and low resolution, barely showing the double-lobe structure of a radio galaxy, with a modern image from the VLA or ALMA, showing intricate details of jet structure, multiple emission components, polarization patterns. It's like comparing a blurry photograph to a high-definition video. The improvement is staggering, and it's driven by advances in technology, algorithms, and our understanding of the underlying physics. Looking ahead, the next decade promises even more revolutionary advances. The square-kilometer array, when fully operational, will be 50 times more sensitive than any current radio telescope. It will detect fainter radio galaxies at greater distances, map larger areas of sky in less time, and study individual sources with unprecedented detail. The ING-VLA, or Next Generation Very Large Array, proposed for construction in the 2030s, will provide resolution 10 times better than the current VLA, allowing us to probe jet structures on scales of light weeks or even light days across. These facilities will transform radio galaxy research. Questions that are currently at the frontier, requiring years of effort to address, will become routine. We'll be able to conduct demographic studies of radio galaxies across cosmic time, understanding how the radio galaxy population has evolved from the early universe to today. We'll watch jets propagate and evolve in real time, observationally speaking, tracking features as they move outward over the course of years. We'll map magnetic fields and measure physical conditions in jets and lobes with precision that currently seems like science fiction. But let's dig into something that doesn't get enough attention: the environmental impact of radio galaxies on their cosmic neighborhoods. When I say impact, I mean it literally. These jets are carrying kinetic energy equivalent to billions of supernovae. When they plow into the intergalactic medium, they create shock waves that propagate outward like cosmic tsunamis. Gas gets compressed, heated to tens of millions of degrees, and accelerated to speeds of thousands of kilometers per second. This has profound consequences for the formation of stars and galaxies in the vicinity. Hot gas can't collapse to form stars. It has too much thermal energy. By heating the gas in galaxy clusters and groups, radio galaxies suppress star formation not just in their own host galaxy but in neighboring galaxies too. Their cosmic birth control, limiting how many new stars can be born across volumes of space measuring millions of light years on a side. But there's a flip side. Shocks can also compress gas, and compressed gas can become unstable and collapse. There's evidence that in some cases, Radio galaxy jets might actually trigger star formation along their paths, creating what astronomers call jet-induced star formation. It's like the universe's most violent form of gardening. You blast the soil with supersonic jets of plasma, and sometimes, in just the right conditions, seeds take root and grow. The evidence comes from observations of young stars and star-forming regions aligned with radio jets, particularly in smaller, less powerful radio galaxies where the jets are interacting with the gas disk of the host galaxy itself. These aren't the giant elliptical galaxies hosting the most powerful radio sources. They're smaller spiral galaxies with active nuclei. Their jets punch through the galaxy's star-forming disk, and in the turbulent wake left behind, new stars are born. This dual nature, destruction and creation, is characteristic of many astrophysical phenomena, and radio galaxies exemplify it perfectly. They're simultaneously shutting down star formation through heating and potentially triggering it through compression. Which effect dominates depends on the local conditions, the power of the jets, the density of the surrounding gas, and a host of other factors that we're still working to understand. Now, here's something that connects to astrobiology in an unexpected way. The cosmic rays accelerated by radio galaxy jets eventually spread throughout galaxies and even into intergalactic space. When these high-energy particles strike planetary atmospheres, they can create chemical reactions, generating molecules that wouldn't otherwise form. On early Earth, cosmic rays may have played a role in creating some of the organic molecules necessary for the origin of life. But there's a limit. Too many cosmic rays would be harmful to life, damaging DNA and other biological molecules faster than they could be repaired. Planets around galaxies with very active radionuclei might receive elevated doses of cosmic ray radiation, potentially making them less hospitable to life. It's a balancing act. You need some cosmic rays to drive interesting chemistry, but not so many that they sterilize your planet. This raises a fascinating question. Does the presence or absence of an active radio galaxy in your cosmic neighborhood affect your chances of developing life? Are radio-loud galaxies less likely to host habitable planets? Or are the effects too small to matter compared to other factors like stellar radiation, asteroid impacts, and planetary geology? We don't know yet, but it's an intriguing area where astrophysics and astrobiology intersect. Let's talk about something called microquasars. These are stellar mass black holes in binary star systems that produce jets, just like their supermassive cousins in radio galaxies, but scaled down by a factor of millions or billions. Microquasars are powered by stellar mass black holes of perhaps 10 to 50 solar masses, accreting matter from a companion star. They produce jets that extend for light years rather than millions of light years. Why are microquasars important for understanding radio galaxies? Because they evolve much faster. What takes millions of years in a radio galaxy happens in days or weeks in a microquasar. We can watch the entire life cycle of jet production play out in human timeframes. Microquasars show state transitions, switching between different accretion modes and jet production states on timescales we can observe. By studying these transitions, we learn about the physics of jet launching and how it depends on the accretion rate and geometry. The beautiful thing is that the same physics applies to both. A 10 solar mass black hole accreting from a companion star and a billion solar mass black hole accreting from the gas in a galaxy center are doing fundamentally the same thing, just at vastly different scales. Magnetic field scale with black hole mass and accretion rate. Jet velocities approach the speed of light in both cases. The relativistic effects are identical. So microquasars serve as laboratories for understanding radio galaxies. We can test our theories of jet production, magnetic field generation, and particle acceleration on microquasars, and then scale up the results to apply to radio galaxies. It's one of the most powerful examples of how astrophysics uses analogies across different scales to build understanding. Here's something about the topology of magnetic fields in jets that's genuinely mind-bending. The magnetic field isn't just a simple dipole like Earth's magnetic field. It's a complex, twisted structure with multiple components. Near the black hole, you probably have a poloidal field component, meaning field lines that run along the jet direction. But as the jet expands and propagates, this field can become helical, twisted into a spiral structure by the rotation of the accretion disk and jet material. This helical magnetic field structure has important consequences. It provides additional collimation, helping keep the jet focused. It affects how particles are accelerated and how they emit radiation. And it creates specific signatures in the polarization of the radio emission that we can observe and use to map out the field structure. Some of the most detailed radio observations of nearby jets show clear evidence for helical magnetic fields, with polarization patterns that rotate systematically as you move along the jet. But here's where it gets really interesting: magnetic reconnection. You've probably heard about magnetic reconnection in the context of solar flares on the sun. It's when magnetic field lines with opposite directions come together and suddenly reconfigure, releasing stored magnetic energy as kinetic energy and heat. This can happen in radio galaxy jets too, particularly in regions where the field is tangled and complex. Magnetic reconnection in jets might be a major mechanism for particle acceleration. The rapid release of magnetic energy can accelerate particles to ultra-high energies almost instantaneously. It might also explain the rapid variability we see in some radio galaxies, particularly blazars. If reconnection events happen in the jet, they could create sudden bursts of energetic particles and corresponding spikes in the radio, optical, and gamma ray emission. There's active research trying to detect and characterize magnetic reconnection in jets. It's challenging because the events are small and fast, even by astronomical standards. But with the right observations at high time resolution and across multiple wavelengths, we're starting to see hints of reconnection-driven activity. If confirmed, it would be a major breakthrough in understanding the microphysics of jets. Now let me tell you about something called frustrated radio sources. These are compact radio galaxies where the jets appear to be confined, unable to break out of the dense gas surrounding the nucleus. Instead of propagating for millions of light years, these jets stall after only a few thousand light years or less, creating compact symmetric objects or CSOs. Why do some radio sources become frustrated while others break out and form giant lobes? It's probably related to the density of gas surrounding the nucleus. If there's a lot of dense gas close to the black hole, perhaps left over from a recent galaxy merger, the jets have to work harder to push through it. They might eventually break out, and these CSOs might just be young radio galaxies that haven't had time to fully develop yet. Or the jets might shut off before breaking out, leaving behind a compact radio source. CSOs are actually quite common, more common than giant radio galaxies, which makes sense if they represent an early phase that every radio galaxy goes through. By studying CSOs, we're learning about the first few thousand years of a radio galaxy's life, the moment of birth when the jets first turn on and start interacting with their immediate environment. There's also the question of duty cycles. How long does a typical episode of radio jet activity last? How much time passes between episodes? These are fundamental questions about the life cycle of radio galaxies, and we're answering them by studying populations of radio sources at different evolutionary stages. CSOs tell us about the beginning. Giant radio galaxies tell us about mature systems. Fading relic lobes tell us about the end. By counting how many sources we find at each stage and estimating how long each stage lasts, we can reconstruct the duty cycle. Current estimates suggest that individual episodes of strong radioactivity last around 10 to 100 million years, with quiescent periods in between that could last hundreds of millions of years or more. But there's a lot of uncertainty, and these numbers probably vary depending on galaxy mass, environment, and merger history. Let's talk about jets in the context of general relativity more explicitly. Near a black hole, spacetime is curved so dramatically that Newtonian physics breaks down completely. General relativity is mandatory, and in general relativity, rotating black holes have some truly bizarre properties. There's the ergosphere we mentioned earlier, but let's go deeper. Inside the ergosphere, spacetime itself is being dragged around the black hole. It's not optional. If you're in the ergosphere, you're being carried around the black hole whether you fire your rocket engines or not. This is called frame dragging, and it's a prediction of general relativity that's been confirmed by experiments with satellites orbiting Earth. But around a black hole, the effect is millions of times stronger. The event horizon, the point of no return, is actually not a single surface for a rotating black hole. There's an outer event horizon and an inner event horizon, and between them, the physics gets extremely weird. Not that anyone could survive the journey to find out, but theoretically, the region between the horizons has properties unlike anything else in the universe. And then there's the singularity at the center. In a non-rotating black hole, the singularity is a point, a location where density becomes infinite and general relativity breaks down. But in a rotating black hole, the singularity becomes a ring of infinite density, spinning inside the black hole. And if you could somehow survive the journey there, general relativity predicts that this ring singularity might act as a portal to other universes or other regions of spacetime. Of course, this is all highly speculative and probably not physically realizable, but it's what the mathematics of general relativity suggests. The jets from radio galaxies are launched from regions just outside these horizons, where spacetime curvature is extreme and relativistic effects dominate everything. The fact that we can observe these jets, study them, and use them to test our theories of gravity and plasma physics is remarkable. Radio galaxies are natural laboratories for extreme general relativity, places where we can test Einstein's theory in regimes that are completely inaccessible in terrestrial laboratories. There have been proposals to use radio galaxy observations to test alternative theories of gravity. If general relativity is wrong or incomplete, and there's some modified theory that better describes reality, then the behavior of matter and energy near black holes might be different. Jets might be launched differently or propagate differently or produce different observational signatures. So far, all observations are consistent with general relativity, which is a triumph for Einstein's theory. But the search continues because finding any deviation would be revolutionary. Now, something about the thermal history of the universe. In the very early universe, shortly after the Big Bang, everything was incredibly hot and dense. As the universe expanded, it cooled. Protons and electrons combined to form neutral hydrogen in an event called recombination, about 380,000 years after the Big Bang. This is when the universe became transparent and the cosmic microwave background was emitted. But then came the Dark Ages, a period lasting hundreds of millions of years when the universe was dark, filled with neutral hydrogen gas and no sources of light except the fading glow of the Big Bang itself. Eventually, the first stars and galaxies formed, and their radiation began ionizing this neutral hydrogen in the epoch of reionization. Radio galaxies from this era, if we can detect them, tell us about the thermal state of the intergalactic medium during reionization. The absorption features in their radio spectra reveal the temperature and ionization state of the intervening hydrogen. By studying many such sources at different distances, we can watch reionization happen, seeing how bubbles of ionized gas grew around the first galaxies and eventually merged to ionize the entire universe. This is frontier science, pushing the limits of what current telescopes can do. But within the next decade, we expect to have a statistical sample of radio galaxies from the epoch of reionization, enough to map out how this critical phase transition occurred. It's like having a time machine, watching the universe transform from dark and neutral to bright and ionized, one observation at a time. Let's discuss something practical. How do we actually identify a radio galaxy's host galaxy? When you observe with a radio telescope, you get a radio source position, but radio telescopes typically have angular resolutions of arcseconds to arcminutes. Even with interferometry, the position might be uncertain by a second of arc or more. And in that small patch of sky, there might be multiple galaxies visible in optical images. So which galaxy is hosting the radio source? Usually, it's the brightest, most massive galaxy near the radio source center, but not always. Sometimes the radio source is offset from the optical galaxy due to jet asymmetries or projection effects. Sometimes there are multiple plausible host candidates, and you need additional observations to figure out which one is right. Astronomers use multi-wavelength observations to solve this puzzle. If there's X-ray emission from the accretion disk, that pinpoints the black hole location. If there's optical emission from an active nucleus, that helps too. Spectroscopy can measure redshifts, confirming that a galaxy candidate is at the same distance as the radio source based on the radiospectral properties. It's detective work, piecing together clues from different wavelengths to build a complete picture. And sometimes we get it wrong. There are cases where a radio source was initially associated with one galaxy, but later observations revealed that the true host was a fainter galaxy nearby, or even a galaxy that wasn't detected in the original optical surveys. As surveys get deeper and more sensitive, we're constantly refining our understanding of which galaxies host radio sources and what properties those host galaxies have. Here's something about the relationship between radio galaxies and other types of active galactic nuclei. We've talked about quasars being radio galaxies viewed down the jet axis, but the picture is actually more nuanced. There are radio-loud quasars and radio-quiet quasars. Radio-loud ones have powerful jets and extended radio lobes. Radio-quiet ones might have weak jets or no jets at all, with the radio emission coming primarily from the accretion disk region. What determines whether an active galactic nucleus becomes radio-loud or radio-quiet? This is one of the biggest unsolved problems in the field. Black hole spin is one candidate answer, as I mentioned earlier. Another possibility is the black hole's accretion rate. Maybe jets only form when the accretion rate is in a certain range, not too high and not too low. Or maybe it's about the magnetic field strength in the accretion disk, which itself might depend on how the black hole is being fed. There's also the question of radio morphology. Among radio-loud sources, why do some become FRI and others FR2? Why do some have straight jets while others are bent or distorted? Why are some sources compact while others have lobes extending millions of light years? Each of these questions probes different aspects of the physics, and answering them will give us a complete theory of radio galaxy formation and evolution. One intriguing idea is that black hole mergers might play a role. When two supermassive black holes merge, the resulting black hole has a spin that depends on the spins and orbital angular momentum of the progenitors. If the merger happens in just the right way, the remnant could have a high spin aligned with the accretion disk, perfect for launching powerful jets. If the merger is more chaotic, the spins might be misaligned or the remnant might have lower spin, leading to weaker or no jets. This connects back to gravitational waves. If we can detect gravitational waves from supermassive black hole mergers and also observe the electromagnetic counterparts, seeing whether the merged black hole subsequently produces radio jets, we'll have direct evidence for or against this scenario. It's a perfect example of how multi-messenger astronomy, combining gravitational wave and electromagnetic observations, can answer questions that neither approach could tackle alone. Let me tell you about intracluster medium, or ICM, the hot gas-filling galaxy clusters. This gas is at temperatures of tens of millions of degrees, hot enough to emit X-rays copiously. It's one of the major baryonic components of clusters, often outweighing all the stars in all the galaxies in the cluster combined. And radio galaxy jets interact with this ICM in spectacular ways. The jets drill through the ICM, creating cavities or bubbles that are visible in X-ray images as dark regions where the hot gas has been pushed aside. These cavities are direct evidence of the mechanical work done by the jets. By measuring the size of the cavities and the pressure of the surrounding ICM, we can calculate how much energy the jets have deposited into the cluster gas. These energy estimates are staggering, often exceeding 10 to 60 ergs, as I mentioned earlier. But here's the kicker. This energy has to be replenished. The cavities rise through the ICM due to buoyancy, eventually mixing with the surrounding gas and dissipating. For clusters to maintain their observed structure, with hot gas not cooling and falling into the central galaxy, the radio galaxy jets must be turning on repeatedly, depositing energy in successive bursts over billions of years. This creates a feedback loop. Gas cools and starts to flow toward the central galaxy. This feeds the black hole, triggering jet activity. The jets heat the gas, shutting off the cooling flow. The jets then shut off and the cycle repeats. It's a self-regulating system, operating on timescales of tens to hundreds of millions of years, that maintains galaxy clusters in a quasi-steady state. The details of how this feedback loop operates are still being worked out. How exactly does the mechanical energy of the jets get converted to thermal energy in the ICM? Is it through shocks, through turbulence, through the mixing of the hot bubble plasma with the surrounding gas? Probably all of these contribute, but their relative importance isn't fully understood yet. There's also the question of metals. The ICM is enriched with heavy elements from supernovae in cluster galaxies. But the distribution of these metals isn't uniform. They're spread out across the cluster, mixed by various processes including radio galaxy jets. By observing the spatial distribution of metals in the ICM using X-ray spectroscopy, we can trace the history of mixing and learn about how efficiently jets stir up the cluster gas. Now let's talk about something called relic radio galaxies. These are old radio galaxies where the jets have shut off, but the lobes are still visible, slowly fading as the particles lose energy. Relic lobes can be identified by their steep radio spectrum, meaning they're much brighter at low frequencies than high frequencies, and by their lack of a clear connection to the central galaxy or any sign of active jets. Studying relics tells us about what happens at the end of a radio galaxy's active life. How long do lobes take to fade completely? What happens to the energetic particles and magnetic fields as the lobes dissipate? Do the lobes simply expand and diffuse away, or do they fragment and mix with the surrounding medium in more complex ways? There's also a population of so-called fossil radiolobes, extremely old and faint remnants of past radioactivity that are barely detectable even with sensitive radio telescopes. These fossils tell us that radioactivity has been occurring in galaxies for most of cosmic history, and that the space around many galaxies is filled with the ghosts of ancient jets. Detecting these fossil lobes requires extremely sensitive low-frequency radio observations because the particles have lost so much energy that they only emit at the lowest radio frequencies. The LOFR telescope, operating at frequencies of 30 to 80 MHz, has been particularly successful at finding these faint, steep spectrum sources. It's revealing a population of past radioactivity that was previously invisible. Here's a connection to philosophy and the nature of scientific explanation. When we observe a radio galaxy, what we're seeing is the result of a chain of causality stretching back millions or billions of years. The black hole exists because the galaxy formed from collapsing gas in the early universe. The galaxy grew through mergers and accretion. One of those mergers brought fresh gas to the central black hole, triggering the current episode of activity. The jets launched millions of years ago based on conditions near the event horizon at that time. The lobes we observe today reflect the integrated history of jet power and environmental interactions over that entire period. In a sense, every radio galaxy is a historical document, encoding information about its past. By carefully analyzing the structure, spectrum, and environment of a radio galaxy, we're doing cosmic archaeology, reconstructing events that happened long before humans existed. This humbling and awe-inspiring simultaneously. We're connecting to events across unimaginable gulfs of space and time, using nothing but the electromagnetic radiation those events produced. Let's talk about something called dying radio galaxies, which sounds morbid but is actually fascinating. These are sources where the jets have recently shut off, perhaps within the last few million years, and we can see the lobes beginning to fade. They have bright, compact cores from past activity but extended lobes that show signs of aging, like steep spectra and lack of active hotspots. What's interesting about dying radio galaxies is that they're rare. At any given moment, most radio galaxies are either actively producing jets or have been off for so long that their lobes have completely faded. The intermediate stage, where the lobes are still visible but the jets have recently shut off, is brief by cosmic standards, maybe only a few million years. So finding dying radio galaxies is difficult, but each one teaches us about the shutdown process and how quickly radio structures dissipate without continuous energy input. There's a related phenomenon called remnant radio galaxies, which are similar but older. The jets have been off for tens of millions of years, and the lobes are very faint and diffuse, detectable only at the lowest radio frequencies. These remnants are important because they represent the final stage before a radio galaxy completely disappears from view. They're also important for understanding the total energy budget of radio galaxies. If you only count actively jetted systems, you might underestimate the total impact of radio galaxies on their environment because you're missing all the energy that went into creating remnants. Now, something about the theoretical challenges in modeling radio galaxies. You might think we could just write down the equations of relativistic magnetohydrodynamics, add in some initial conditions representing a black hole and its environment, and let a computer simulation run. And we do that, but the problem is the enormous range of scales involved. The event horizon of a supermassive black hole might be a few light hours across. The lobes of the radio galaxy can be millions of light years across. That's a ratio of about 1 billion in linear size, or 10 to 27 in volume. No computer simulation can possibly resolve all these scales simultaneously. We have to make choices, either simulating the small-scale physics near the black hole in detail while ignoring the large-scale structure, or simulating the large-scale jet propagation while simplifying the jet launching mechanism. This is where analytical theory remains important. Clever approximations, scaling laws, and order of magnitude estimates can bridge these scales in ways that pure simulation cannot. The art of theoretical astrophysics is knowing when to simulate and when to calculate, when to seek exact solutions and when to be satisfied with approximate ones that capture the essential physics. There's also the problem of turbulence. Turbulent flows, whether in gases or plasmas, are notoriously difficult to simulate accurately. Turbulence involves structure on all scales simultaneously, from the largest eddies down to the smallest dissipation scales. Radio galaxy jets are almost certainly turbulent, at least in some regions. That turbulence affects how particles are accelerated, how magnetic fields are amplified, and how the jets interact with their environment. But accurately simulating turbulence requires tremendous computational resources and sophisticated numerical methods. Let me tell you about the connection between radio galaxies and the thermal Sunyaev-Zel'dovich effect. This is a subtle effect where the hot gas in galaxy clusters scatters photons from the cosmic microwave background, slightly changing their energy distribution. It's a way of detecting galaxy clusters through their hot gas, independent of their distance. Radio galaxy jets heat the cluster gas, as we've discussed. This heating directly affects the thermal Sunyaev-Zel'dovich signal. By comparing radio observations of jets and X-ray observations of hot gas with Sunyaev-Zel'dovich observations of the same clusters, we can study the heating process in unprecedented detail. We can see how energy from the jets is distributed through the cluster, how it affects the temperature structure, and how efficiently mechanical energy is converted to thermal energy. Some of the most detailed studies combine all three observational approaches: radio for the jets, X-ray for the gas, and microwave for the Sunyaev-Zel'dovich effect, creating a complete picture of energy flow in galaxy clusters. It's a beautiful example of how different observational techniques complement each other, each providing information that the others cannot. Here's something about the history of radio galaxy research that illustrates how science progresses. In the 1960s and 1970s, there was serious debate about whether radio galaxies were really at the enormous distances indicated by their redshifts. Some scientists proposed that perhaps the redshifts were not cosmological, that these objects might be much closer than they appeared. This was part of a larger controversy about quasars and active galactic nuclei. The controversy was settled by accumulated evidence. Galaxies were found at similar redshifts near radio galaxies, confirming they were at cosmological distances. The energetics worked out if the sources were distant, but not if they were nearby. The statistical properties of radio source counts matched cosmological models. Gradually, the non-cosmological redshift hypothesis was abandoned because it couldn't accommodate the full range of observations. This is how science works. Controversial ideas are proposed and vigorously debated. Evidence accumulates. The idea that best explains all the evidence wins, not through authority or decree, but through the weight of observational and theoretical arguments. Radio galaxies played a crucial role in establishing the cosmological nature of active galactic nuclei, helping to build the consensus that now forms the foundation of modern astrophysics. Let's discuss jets at very high energies, the gamma-ray emission we touched on earlier. Gamma rays are the most energetic form of electromagnetic radiation, with photon energies exceeding millions or even billions of electron volts. Producing gamma rays requires extraordinary physical processes, and radio galaxy jets have several mechanisms available. One is inverse Compton scattering, where relativistic electrons in the jet collide with lower energy photons and boost them to gamma-ray energies. The photons being scattered could be from the cosmic microwave background, from starlight in the host galaxy, or even from the jet's own synchrotron radiation. Each possibility produces a different gamma-ray spectrum and variability pattern. Another mechanism is hadronic processes, where relativistic protons collide with photons or other particles, producing pions that then decay into gamma rays and neutrinos. This is more speculative but potentially very important because it would mean jets are accelerating protons, not just electrons, to ultra-high energies. Neutrino observations would be the smoking gun evidence for hadronic processes. The Fermi Gamma Ray Space Telescope has detected hundreds of active galactic nuclei in gamma rays, mostly blazars but also some radio galaxies. The gamma ray emission is highly variable, changing on timescales of hours to days in some cases. This rapid variability constrains the size of the emission region to be very small, light hours to light days across, right at the base of the jet near the black hole. By studying how the gamma-ray emission correlates with radio, optical, and X-ray emission, we can build up a picture of what's happening in different parts of the jet simultaneously. Sometimes the gamma-ray flares happen at the same time as radio flares, suggesting they're produced in the same location. Other times they're uncorrelated, suggesting multiple emission zones along the jet. It's complex, but every observation adds a piece to the puzzle. Now, something about the morphological diversity of radio galaxies that we haven't fully explored. Beyond the basic FRI and FR2 classification, there are Z-shaped radio galaxies with jets bent at sharp angles, S-shaped galaxies with curved jets, galaxies with one jet much brighter than the other, galaxies with jets that seem to wiggle or precess, and galaxies with multiple sets of lobes at different position angles. Each morphology tells a story. Z-shapes might result from sudden changes in jet direction due to black hole mergers or gravitational perturbations. S-shapes could indicate jets propagating through a rotating medium or orbital motion of the host galaxy. One-sided jets might simply be a relativistic beaming effect where the jet approaching us is much brighter than the receding jet. Wiggling jets suggest precession of the black hole spin axis or instabilities in the jet launching mechanism. By cataloging these morphologies and comparing them to theoretical models, we learn about the detailed physics of jet production and propagation. Nature has performed millions of experiments for us, creating radio galaxies with every possible combination of parameters. Our job is to observe them all and figure out what each variation is telling us. Let's talk about the role of environment more explicitly. A radio galaxy in a rich cluster, surrounded by dense hot gas, will evolve differently than a radio galaxy in a poor group or in isolation. The dense environment confines the lobes, making them smaller and more compact for a given jet power. It also provides more material for the jets to interact with, creating more prominent hotspots and shocks. Conversely, a radio galaxy in a low-density environment can expand more freely, creating larger lobes for the same jet power and lifetime. The environmental density also affects how long it takes for the lobes to fade after the jets shut off. In dense environments, the lobes might be compressed and dissipated more quickly. In low-density environments, they could persist as detectable remnants for much longer. There's also the question of where radio galaxies preferentially occur. They tend to be found in massive elliptical galaxies, which themselves tend to be found in groups and clusters. So radio galaxies are not uniformly distributed across the universe. They're concentrated in regions of high galaxy density. This clustering has to be taken into account when doing statistical studies of radio galaxy properties and evolution. Here's something about the future that's particularly exciting: artificial intelligence and machine learning applied to radio galaxy research. Modern surveys are producing so much data that traditional analysis methods can't keep up. Automated classification, anomaly detection, and pattern recognition using neural networks and other machine learning techniques are becoming essential tools. Machine learning algorithms have been trained to classify radio galaxies by morphology, to identify interesting or unusual sources in large surveys, and even to predict physical properties like redshift or jet power from the radio images alone. These algorithms don't replace human astronomers, but they augment human capabilities, handling the routine classifications quickly so that humans can focus on the most interesting and unusual objects. There's also the potential for machine learning to discover patterns in the data that humans might miss. Maybe there are subtle correlations between radio morphology and host galaxy properties, or between jet power and environmental characteristics, that are too complex for traditional statistical methods to uncover, but that a sufficiently sophisticated neural network could learn. We're just beginning to explore these possibilities. One particularly promising application is using machine learning for removing foreground contamination in radio images. Radio observations often pick up emission from our own galaxy, from ionospheric effects, or from radio frequency interference from human technology. Removing these contaminants to reveal the true signal from distant radio galaxies is challenging. Machine learning algorithms trained on clean and contaminated data can learn to identify and remove contamination more effectively than traditional methods. Now let's discuss something profound about the nature of observation itself. When we observe a radio galaxy billions of light years away, the radio waves we're detecting left the source billions of years ago. They've been traveling through expanding space all that time, gradually shifting to lower frequencies due to the cosmological redshift. They've passed through the intergalactic medium, possibly through multiple galaxy clusters, scattering off electrons and being affected by magnetic fields. By the time they reach Earth, these radio waves carry information not just about their source, but about everything they encountered along the way. In a sense, every radio observation is a line-of-sight probe through cosmic history. By carefully analyzing the signal, we can learn about the intergalactic medium, about the distribution of matter and magnetic fields, about the expansion history of the universe, all in addition to learning about the radio galaxy itself. This is why radio astronomy is so powerful. A single observation gives you information about many different astrophysical phenomena. You just have to know how to extract it, how to disentangle the effects of the source from the effects of propagation, how to separate foreground from background, signal from noise. Let me tell you about radio galaxies and cosmic magnetism. One of the big questions in cosmology is, where did galactic and intergalactic magnetic fields come from? We observe magnetic fields everywhere we look in the universe, in stars, galaxies, galaxy clusters, even potentially in the voids between clusters. But the origin of these fields is unclear. Were they primordial, created in the early universe? Or did they develop later through dynamo processes in the first stars and galaxies? Radio galaxies might be part of the answer. The jets transport magnetic fields from their host galaxies out into the intergalactic medium. Over cosmic time, with many radio galaxies pumping out magnetized plasma, the intergalactic medium could become seeded with magnetic fields. These seed fields could then be amplified by turbulence and structure formation, eventually producing the widespread magnetism we observe today. There's evidence for this scenario from observations of Faraday rotation in radio sources at different distances. The strength of the intergalactic magnetic field seems to correlate with the density of galaxies and the history of radio galaxy activity. Regions that have hosted more radio galaxies over time show stronger magnetic fields. It's circumstantial evidence, but it's consistent with radio galaxies playing a role in magnetizing the universe. This would be yet another way that radio galaxies shape their environment on the largest scales. Not just heating gas and suppressing star formation, not just enriching the intergalactic medium with heavy elements, but also creating and amplifying the cosmic magnetic fields that thread through all of space. Here's something about the practical applications of radio galaxy research that's worth mentioning. Developing the technology and algorithms for radio astronomy has spin-off benefits for society. The signal processing techniques used to extract faint radio signals from noise have applications in medical imaging, telecommunications, and many other fields. The data analysis methods developed for handling huge radio survey datasets are relevant to big data challenges across science and industry. Radio interferometry has directly led to advances in GPS technology, earthquake monitoring, and precision measurement. The computational techniques for radio image reconstruction have influenced fields ranging from computer vision to machine learning. Science doesn't just produce knowledge. It produces tools, methods, and trained people who then apply their skills across society. And beyond practical applications, there's the inspiration factor. Radio galaxies, black holes, cosmic jets spanning millions of light years. These capture the imagination in ways that few other scientific topics can. They inspire young people to pursue careers in science, technology, engineering, and mathematics. They remind us that the universe is far more amazing than our everyday experience suggests, that there are wonders beyond imagining waiting to be discovered. Now let's come to something deeply satisfying about radio galaxy research: the convergence of evidence from multiple lines of inquiry. We don't understand radio galaxies from one observation or one theoretical calculation. We understand them because radio observations agree with X-ray observations, which agree with optical spectroscopy, which agree with theoretical models, which agree with computer simulations. When multiple independent approaches all point to the same conclusion, we can be confident we're getting something right. This is the strength of the scientific method. No single piece of evidence is definitive. There are always uncertainties, ambiguities, potential errors. But when many pieces of evidence, each with their own uncertainties, all align to tell the same story, the probability that the story is correct becomes very high. Radio galaxies are powered by supermassive black holes. They launch relativistic jets through magnetohydrodynamic processes. They affect their environment through mechanical feedback. We know these things with confidence because the evidence from many sources agrees. Yet there's still uncertainty, still room for surprise. Every assumption we make could be wrong. Every model could be missing something crucial. That's what makes science exciting. We're always probing the boundaries of our knowledge, always looking for the observations that don't fit, the anomalies that point toward new physics. As we've explored in this cosmic journey, radio galaxies represent one of the universe's most spectacular phenomena. They're laboratories for extreme physics, natural experiments in black hole behavior, and relativistic plasma dynamics. They're shapers of cosmic evolution, regulating how galaxies and clusters grow and evolve. They're probes of the universe's history, tracers of cosmic structure and evolution across billions of years. Every radio galaxy we observe is unique, with its own history, its own peculiarities, its own story to tell. Yet they're all manifestations of the same underlying physics, the same fundamental processes operating across a huge range of scales and conditions. This combination of diversity and unity is what makes them so endlessly fascinating to study. The field has come so far in the decades since Carl Jansky first heard that mysterious hiss from space. We've gone from crude detections to exquisite images revealing structure on every scale. We've gone from wondering what these objects might be to having detailed physical models of how they work. We've gone from studying a handful of sources to having catalogs containing millions. And yet, in a very real sense, we're still at the beginning. The upcoming generation of radio telescopes will revolutionize the field once again. The Square Kilometre Array, the next generation Very Large Array, and other facilities will reveal radio galaxies in unprecedented detail and discover new ones by the millions. Each new observation will test our theories, challenge our assumptions, and potentially reveal new phenomena we haven't even imagined. The questions that keep researchers awake at night are evolving. How did the first supermassive black holes form? What determines whether a black hole produces radio jets? How do jets maintain their collimation across millions of light years? What exactly happens in magnetic reconnection events in jets? How efficiently do jets accelerate particles to ultra-high energies? What's the complete life cycle of a radio galaxy from birth to death and potentially rebirth? We have partial answers to all these questions, but the full picture remains elusive. Every answer leads to new questions. Every solved mystery reveals new puzzles. That's the nature of scientific progress. We're not moving towards some final understanding where all questions are answered. We're exploring an infinitely rich landscape where every peak climbed reveals new peaks beyond. Radio galaxies connect to nearly every area of modern astrophysics. Cosmology, galaxy evolution, black hole physics, plasma physics, particle acceleration, magnetic fields, the intergalactic medium, cosmic structure formation, even potentially astrobiology. They're not isolated curiosities. They're integrated into the larger story of how the universe works. And here's what truly remarkable: we figured all this out by listening, by building antennas, pointing them at the sky, and carefully analyzing the faint radio whispers reaching us from billions of light years away. The universe is broadcasting its secrets constantly, and we've learned how to tune in. When you look up at the night sky, your eyes see stars, perhaps a few planets, maybe the band of the Milky Way if you're lucky enough to be away from city lights. But if you could see radio waves, the sky would be transformed. Bright radio galaxies would dot the heavens, their enormous lobes glowing brilliantly. Blazars would flare and vary. Supernova remnants would shine. The galactic center would blaze with activity. The cosmic microwave background would bathe everything in a faint glow. We can't see radio waves with our eyes, but we've built instruments that can. And through those instruments, we've discovered an invisible universe, just as real and just as rich as the visible one. Radio galaxies are citizens of that invisible universe, and by studying them, we're learning to see with more than our eyes. The story of radio galaxies is ultimately a human story. It's about our curiosity, our drive to understand the universe we inhabit. It's about our ingenuity in developing the tools and methods to observe the unobservable. It's about our persistence in the face of difficult problems and confusing data. It's about our willingness to be surprised, to have our assumptions overturned, to follow the evidence wherever it leads. Every astronomer who has contributed to our understanding of radio galaxies, from Carl Jansky hearing that first mysterious signal to the researchers working today pushing the boundaries of what we know, has added to this collective human achievement. They've expanded our cosmic horizons, revealed the workings of nature on scales both tiny and vast, and given us new perspectives on our place in the universe. And the story continues. Right now, telescopes around the world and in space are observing radio galaxies, collecting data, making discoveries. Students are analyzing that data, writing their theses, preparing the next generation of insights. Engineers are designing the next generation of instruments that will take us even further. Theorists are developing new models, running new simulations, predicting what we might find next. The universe has been launching radio jets from supermassive black holes for billions of years, long before Earth existed, long before life emerged, long before humans evolved and developed the ability to wonder about such things. These cosmic phenomena were happening in the darkness of deep space, unseen and unsuspected, for almost the entire history of the universe. But now, in this brief moment of cosmic time, we're here. We're observing, measuring, understanding. We've turned our attention outward and discovered radio galaxies in all their magnificent complexity. We're using the light, or in this case radio waves, from the distant past to reconstruct cosmic history, to understand how the universe has evolved and how it works. In a universe billions of years old and billions of light years across, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, it might seem that nothing we do matters, that we're insignificant specks on a speck of a planet orbiting an ordinary star in an ordinary galaxy. But we're the specks that figured out what radio galaxies are. We're the specks that can observe across billions of light years and reconstruct the detailed physics of jets launched from supermassive black holes. We're the specks that can wonder, that can discover, that can understand. That's not insignificance. That's something extraordinary. In the vastness of space and time, The universe has produced structures capable of looking back at themselves and comprehending their own nature. Radio galaxies are part of that structure, and so are we. We're all made of the same atoms, forged in the same stellar furnaces, governed by the same laws of physics. The universe is not something separate from us that we observe from the outside. We're part of it, a way for the universe to know itself. Radio galaxies teach us humility. They show us how much larger, more powerful, and more spectacular the universe is than our everyday experience suggests. They remind us that Earth and humanity are recent, fragile, tiny parts of an ancient, vast, and often violent cosmos. But they also teach us confidence. They show us that despite our limitations, we can understand even the most extreme phenomena in the universe. Our minds, though small, can comprehend the immense. Our theories, though imperfect, can describe reality with remarkable accuracy. Looking forward, the next decades promise revelations about radio galaxies that will likely surprise and delight us. There will be discoveries we can anticipate and plan for, but also discoveries we cannot imagine because they'll reveal phenomena we haven't yet conceived of. The history of astronomy is full of serendipitous discoveries, unexpected findings that open new fields of research. Radio galaxies themselves were one such discovery, completely unanticipated before radio astronomy began. What will the next surprise be? Will we find radio galaxies with properties that challenge our current theories? Will we detect the first radio galaxies from the epoch of reionization, seeing black holes at work when the universe was in its infancy? Will we observe a supermassive black hole merger in real time, catching both the gravitational waves and the electromagnetic fireworks? Will we discover that jets play an even more important role in cosmic evolution than we currently appreciate? We don't know, and that's thrilling. That's why we keep building telescopes, keep making observations, keep pushing forward. Because we know there's more to discover, more to understand, more surprises waiting for us in the data yet to be collected. So here we stand, inhabitants of a small planet orbiting an ordinary star, using instruments made of metal and silicon and clever engineering to detect radio whispers from black holes billions of light years away. We're listening to the universe, and increasingly, we're understanding what it's telling us. Radio galaxies are part of that cosmic conversation, broadcasting their signals across space and time. And now, finally, after billions of years, someone is listening and comprehending. This is the wonder of radio galaxies, the marvel of science, and the triumph of human curiosity. The universe creates these spectacular phenomena, and we get to study them, to figure them out, to tell their stories. In doing so, we're writing our own story, the story of a species that looked up at the sky and wondered, that built instruments to see what couldn't be seen, that refused to accept ignorance when knowledge was possible. Radio galaxies are out there right now. As you finish listening to these words, launching their jets, inflating their lobes, affecting their environments across millions of light years. They don't know we're watching. They don't care. They simply are doing what the laws of physics compel them to do. But we know. We watch. We care. And in that knowing, that watching, that caring, we participate in one of the great adventures of human existence. The quest to understand the cosmos and our place within it.